Okay, thank you very much, Nat, and thank you to the Geological Society for inviting me down here today. As Nat said, I'm going to be talking about the extraterrestrial, okay, from meteors to micrometeorites. But I should point out, to start with, that when it comes to my research career, it has been varied, but if I was to categorize myself, I would categorize myself as a geochemist who has studied the majority of their career past paleoclimates. So understanding how climate has changed back through the geological record. Okay? And that's where I've spent the majority of my time in some amazing places, including two locations here. This is up in Tremp, up in the northeast of Spain. And both of these images here show a very famous horizon here, which is called the Claret Conglomerate, in which a major climate event happened in the past. Okay? And for years, you'd find me working in field areas like this and other sites around the UK. But as the cartoon shows there is a point in everybody's life where one feels that they need a change. Okay? I'm not saying it was a midlife crisis, okay, but if there's an academic version of that, it probably was. I needed to try something new because I'd spent the majority of my career investigating essentially the same events. So I decided to have a change, and that change was not the most radical change, okay, a bit like Snoopy here. I just decided to pivot somewhere else. But before committing to a new research area, and I will get back to my research right at the very end of this talk, before completely committing, I decided to investigate this new field as a citizen scientist, okay? Because outside of my academic role, I like to keep myself busy during the weekends, during the week, and during the weekends, okay? But being a scientist, I like to keep myself busy doing something which I feel is contributing as well. Okay? So I got involved in a number of citizen science projects. And I will say, before I say too much about those two projects, is you don't need to be a scientist to be a citizen scientist. Okay? You just need to be a citizen. Okay? All I'm going to talk about today is two fields that have been designed and work for citizens, so just the general public. If you are a scientist already, that's just sheer coincidence. Okay? So what I'm going to talk about are two things: the Global Meteor Network, okay, what it is, and how I got involved in it, okay? And then we're going to pivot onto micrometeorites, okay, what they are, how I collect them, and why they're important. Okay. So starting off with the Global Meteor Network, what is the Global Meteor Network? Well, before we get onto it, just a few key words I'm going to use throughout this talk, okay? So I'm going to talk about comets, asteroids, meteoroids, definitely meteors, okay, fireballs, and then meteorites, okay? And this is from the Canadian Space Agency, and they're just a classification of what each of those different terms are. The most important for us is the meteors, which are what actually streak through the atmosphere, so these are the shooting stars, and if they're large enough, they become fireballs, and then if they make it through the atmosphere and land, then they become meteorites, okay? And I'll be talking about both of them. Also, just a plug, if you ever do think you find a meteorite, there is actually from the Fireball Alliance, the UK Fireball Alliance, there is some advice about what to do. So if you are lucky enough, and I'll talk about an example where a citizen actually did find a meteorite, it actually landed on their driveway, okay, so they didn't even have to go far to find it, okay. What to do if you find one. And then finally, if you haven't seen this film, don't look up. I would really highly recommend you please go and watch it. It's just a huge parody on life at the moment, okay, and especially society at the moment. The reason I put it up here is I'm not saying don't look up. I'm actually saying completely the opposite. Look up, look into the night sky. There's so much going on out there, okay, and also so much coming through that you probably are not aware of that you can get involved in as citizen scientists. So going back to the Global Meteorite Network, so what is the Global Meteor Network? Well, as the name entails, okay, it's a global network of meteor cameras that are looking up in the night sky, okay? And it has a really bold mission, and that is no meteors unobserved, okay? I say it's bold, and hopefully it will eventually become true. But on this global map here, we have the distribution of all of the meteor cameras as part of this global meteor network. They're the blue dots, okay? And as you can see, it's not quite completely global at the moment, okay? There is a good and a reasonable coverage around Western Europe, okay, including the UK. You can't actually see the UK because there's so many meteor cameras in the UK. And that means, I'm not saying don't get involved in this if you still live in the UK. More cameras are better, okay? But we have essentially the UK covered. Okay? Western Europe is quite well covered as well. A bit in Western Australia, New Zealand as well. And then the west coast of the US. But there are huge areas around the globe which are essentially dark spots, okay, which are not included in this network. And hopefully by promoting it, I'm not saying I'm going to cause this, but hopefully by promoting it, which the network does, we can expand those cameras more globally as well. Okay. The UK arm of the global meteor network, surprisingly, is called the UK Meteor Network, okay? And it has its own organization, its own society, its own governance, it's a charity, okay? And on this map here shows the distribution of the UK Meteor Network, okay? We've got a couple of ones across the channel as well, okay, looking our way. But essentially, these are all the cameras in the UK. And I'm Plymouth, so we're down here somewhere. That's my cameras down here. But using all of those cameras, we've got a fair distribution or fair coverage over the whole of the UK. Okay? And just to say, it was set up in about 2012, and the network now has approximately 200 plus cameras. There's constantly cameras coming online and then going offline, but in general, it's around 200 cameras now. And as you'll see when I show you my distribution, where my cameras look, we've literally got the whole UK covered with all 200. So this is me here in Plymouth, okay? Actually, this is me sitting on my roof, which is just up there somewhere, okay? Installing my cameras. And I have 3 cameras. I have a camera that looks to the east and southeast, a camera that looks to the northeast, and then one looks roughly west. And this is the area, this is the sky I can cover, my cameras cover, at about 100 kilometers altitude. Okay? I don't have a camera pointing in this direction, in other words, this direction here, because I have a huge tree here, and a flat, so a block of flat. So I can't actually got a good view of the sky there. If I didn't, I would have another camera on this corner of the dormer here, okay? Should point out, how do you join? So if you want to join the network, you can contact, they have a website, you can look on the website, and they will tell you how to build your own camera. And the whole idea about this is not, and this is why I got involved in it, is it's not only about the data that you are collecting and contributing to the network, it's about just the exploration, about building cameras, getting the setup right, and I'll talk about the setup in a bit, okay? And even doing some basic computing, because the whole of this network, okay, runs off one Raspberry Pi computer. Yes, you can have other Linux computers, but if you've got a Raspberry Pi computer, you can set up your own network. Okay? The cameras that we tend to use are this type, so it's a Sony camera with an IMX sensor, okay, and it has about a 45-degree angle of view, each of those cameras. And each photo, so it constantly takes photos at night. Each photo is made up of about 256 frames. So it means that they can, in one photo, they can subdivide that photo up and see the actual meteor coming in at different points during that photo. Okay. I am a little bit concerned, or I should point out my wife is a little bit concerned, who I think is watching online, so hello, Olivia. I've drilled so many holes into the side of my dormer window at the top of my house that if we ever move out, well, when we do eventually move out, okay, I'm going to be patching up screw holes everywhere. And it's whether we tell our buyer of our new house that their dormer frame is full of holes inside. Anyway. So anyway, after you get your camera set up, so you buy the parts, the list of the parts are available online. You order them. The instructions about how to build the camera, the security camera, is online as well. You build it together, and then you attach it to your house, and you point it up at the sky. It roughly about just short of a 45-degree angle is the best angle to have, with as much uninterrupted sky view as possible. But as you can see here in this one here, this is looking back over my house. This is the roof of my house. You're always going to get a bit of roof or a bit of a tree or something in there. So the first thing you need to do is create a mask online, which essentially just tells the operating system, which is run on the Raspberry Pi, to ignore anything that's happening in these parts here. And then secondly, which is the critical bit, it will photograph regularly throughout the night. But if you want to contribute data to the global meteor network, the operating system needs to know where it's looking, okay? At what time and at what angle, okay? So you have to create a calibration file, or what's called a plate path file, okay, which uses some freely available online astronomical software, SkyFit2, and you create that file so every night the camera knows what it's looking at, and it's got an orientation, declination, and elevation as well. Okay? So once you've created those two, okay, you can essentially just let your camera loose. Every night there's no clouds, okay, which in the UK I know is not every night, okay, but if there's no clouds in the UK and it can see the stars, it needs to see at least 20 stars, okay, recognized in that plate path file to actually work out where it is. But as long as you can see all 20, okay, then it will start capturing images. And actually, it will capture images even if you don't have a calibration file. So if all you're interested in is looking through your image file the next day and seeing if you've caught some nice fireballs, okay, this one, 2005, or and the one here from 2025, okay, then you can essentially just leave the camera running. Okay? But if you want to contribute to the citizen science project, the global meteor network, then you need to have it calibrated. Okay? So usually you have to collect 2 or 3 days or 2 or 3 nights worth of information, data, before they will allow your stream to go in to the network as part of that collection. Okay? What I really like about it is if you get so here is one of the meteor showers. So this is the Perseid meteor shower, 11th of August. This was a couple of years ago now, or just short of a couple of years ago. And actually, this is a stack of all of the detections it had from that night. And in one night, my camera, that was this case looking west, caught over 112 meteors in one night during that shower. Okay? And I think just those stacks themselves make really good images. Okay? The thing, though, is those cameras capture everything that's going on. Okay? What you'll get at the end of each day is you will get a capture stack, so everything is captured. Any kind of movement in the sky, it will capture and save that image. And then it will have a detection stack, where it looks at those captures in a little bit more detail to work out if it is likely to be a meteor or not. And that detection stack that I showed you in the last image, okay, those 112, were just the ones that it confirmed as likely to be meteors, okay, or shooting stars. This is a capture stack, okay, that shows it captures everything that's going on in the night sky. So in here we have some aeroplane trails. Okay, these what these solid lines are here. Okay, we have a few meteors here. We actually have some star trails. Okay, here the celestial north is just over there somewhere, where the center of these star trails. Rather annoyingly, you also capture Starlink satellites. Every time Starlink satellites come across, they're rather bright and annoying. Okay, and we capture those as well in our capture stack. But we capture other things as well, other unique things as well. This, you can just about make it out here. I don't have the best images of these. There are certain cameras in the network that have hundreds, thousands of these. This is a bat. Okay? So when a bat flies across the image, it's just got enough reflection on its wings to actually be recorded in that image. And I've always wondered, and I've been trying to some of my colleagues at the university to see if it's actually worth interrogating this data for bat population surveys. Okay? So instead of just using sound, okay, going out and recording their calls, I was going to call them squeaks, but that's probably unfair on bats. Okay? We could also use images like this, because this is the total stack. Okay, I've only got one bat, but other ones, they've got thousands of bats. Okay? So it could be used for that. One other thing I did only once capture, and I was very lucky to as well, were these things here. This, really low on the horizon, is sprite lightning. So these are very high up, lightning very high up in the mesosphere, but it's low on my camera because it's very far away, if you follow what I mean. Okay? And essentially, this is lightning that goes up. Okay, you sometimes see these from the space station and satellites showing lightning literally going up from the atmosphere into space. And our cameras, the UK Meteor network and the global ones as well, have caught really nice examples of these. And of course, being a citizen scientist, as soon as I got those, I contributed my images to become a spectacular citizen scientist, which is a network that just captures all of these images of sprite lightning. Before anybody asks, okay, it may or may not come up as a question, no, I have never caught a UFO on camera. Okay? Well, not that I'm aware of anyway. Okay, the system doesn't recognize. There's nothing obvious floating across my screen or across my images, so I haven't caught anything like that. But what I did catch in 2024, and this was really lucky as well, this is a, so you can break down those capture stacks into individual images. So this is for about 11 o'clock at night up to just short of midnight, okay? It looks like all of these images here are very fuzzy. That is not clouds, okay? That, by sheer coincidence, I happen to have my other camera pointing out the window, which is just a Canon camera capturing the photographs around. That was the Aurora Borealis, which was a spectacular display for Plymouth. Okay, we are so far south. Okay, we shouldn't see the Aurora Borealis.
Where do you live?
Down in Plymouth. Okay, so down on the south coast. So to get something like that happening, okay, it was a really large magnetic storm. Okay, but the Meteor network can capture it as well. And there was, after this happened, and those people who didn't have color cameras pointing out at the sky at those nights, there was a big debate in the network about why can't we make our Meteor cameras color cameras? Okay, because we'll then be able to capture really nice images of the Aurora Borealis, especially those cameras up in Scotland and Northern England, etc. They did trial that, so the network did trial that, but the resolution, okay, the capture resolution in color is much lower than in black and white. So they were losing a lot of the data, okay, about meteors coming through the atmosphere. So they decided to stick with the black and white cameras. So at the end of the day, okay, what happens is if you're in the network and you're contributing to it, every day you will receive a report, or we do in the UK anyway, you will receive a report from a guy called Mark McIntyre, who's part of the network, which outlines the top 100 captures that day. Okay? And you can click on those captures, and it will show you information about that meteor that you've captured. So first of all, to actually count as a capture and to work out the orbital direction of this meteor, so where it came from in the solar system and where it was going as it was coming through the atmosphere, you need to have at least 2 cameras, okay? Ideally from different angles, views of it. So if you have more than 2 cameras, then you can work out a orbital trajectory, okay? And you get that information, you can interrogate that information. Should point out as well that information is freely available online. Okay, so I'll mention a website at the end, happens to be my website, my outreach website, okay, that has links to all of these data sets. So if you are interested in interrogating past events, you can go and look and find these individual reports for past meteor events. Yeah? But it gives you the orbital trajectory, whether it's part of a known meteor shower, or whether in this case, whether it's a sporadic fireball that just came through the atmosphere. So how good is the network? Well, as I said, it all depends on the number of cameras. More cameras you have, the greater number of chances of you actually capturing meteors in there. Okay? And from about 2025, there's roughly been about 200, and we've had over 1 million detections from those cameras. And 137,000 of those have been determined, or we've been able to, or the network has been able to calculate the orbital parameter of them. In other words, where they came from in the solar system and where they were going as they entered our atmosphere. And in 2025, 46 of those were what we would class as fireballs. So bright enough to potentially have a fall associated with that. There's one disadvantage about the network. It doesn't quite, the one bit it does stumble on when it's doing its automated capture to detection is if it is a really bright fireball. It gets a bit confused and sometimes can miss those. So we're encouraged to go in every day and also look at our results to make sure that there isn't a big fireball that's been missed. And there has been, on occasions, really bright fireballs. The detection system has essentially gone, I give up, I don't know what that is, okay, and not done anything. But once they can be identified, okay, then we can, or the system can manually process that data itself. Okay. So yeah, it's quite, I think it's quite a success, okay? But you can see how the number of matches has built over time as the number of cameras in the system have built over time. And when it comes to what happens to that citizen science data, well, as I said, it is data. That data does contribute to ongoing research. So there is ongoing research into using that data, and as I said, that data is freely available. I got mentioned, okay, there I am, in this paper here. I should point out that's probably the 3rd page of 7 acknowledgements, because they listed everybody in the network. But hell, okay, I've got an acknowledgement in a paper on the Meteor network, and I'm happy about that. But it also, what they do is they detect new meteor showers, okay? They work out flux measurements, so what is the meteor flux? NASA, space agencies are always interested in that, so that contributes to that data set as well. And the network is really engaged and involved. So it actually has its own youth section to it, and it actually has a meeting. So the 2026 Global Meteor Network meeting, okay, is online, it's hybrid, okay, and if you're a member, you can go to that. But why did I really get involved in the Global Meteor Network? Was it because I really wanted to get my name on a paper about the flux estimates? Okay, deep down, I wanted to play with something new. I wanted to build something. I wanted to collect new data. I wanted to be involved in something that was new to me. But I think deep down, what I also wanted to do was to find a meteorite. Okay, and the Global Meteorite Network does get involved in capturing or working out falls. And the most famous in the UK is probably the Winchcombe meteorite. So I mentioned at the beginning that some of these fireballs make it all the way down. Well, in 2021, one did, and it literally landed on this couple's driveway, Will Cox's driveway, and became a world-famous meteorite. Okay? And some in this room have actually worked on that. And a sample of that is actually available in the Natural History Museum if you want to go and see this meteorite. Okay? And the Global Meteorite Network actually helped work out where the fall zone was for that meteorite above and beyond the bit that literally landed on somebody's driveway. Okay, so what area around, in this case, Winchcombe, was a search area. And it helped search teams go out into the local fields with the permission of landowners to find more examples of these meteorites. Yeah. There was a recent one in Scotland as well, okay, which came down in 2025, okay, where this is the light flight, so this is from the meteor network, and then they calculated based upon wind and atmospheric conditions where the dark flight zone was and where likely fall material was. Unfortunately, even though University of Glasgow team went out to look for this, okay, they were unable to identify any fall material. Okay? But they have put out a call if anybody's up in this region, okay, and you're walking around. It is very isolated, I should point out, okay, and it's landing in heather and I don't think it's bog, but quite difficult terrain to find a fall in. But if you do, if you're up there, or when somebody's listening online and they're up there, okay, then please, if you do find something, okay, follow the advice and then maybe contact the Glasgow University group and Natural History Museum yeah, let them know that you found something. In Plymouth, I got really excited about in just the end of 2025, okay, because there was a fireball that was caught on my camera, okay, and I got really excited because they did a calculation of where a potential fall zone was, and for a bit, it was going to be somewhere around here, around Padstow, and I had all these plans to take my students up there and to go looking for it. And then they recalculated the dark flight zone, and yeah. Let's just say I didn't fancy going swimming, okay? And problem is, this is the problem when you live in Plymouth, okay? And you get meteor falls down in the southwest, unless it literally is going this way or that way, the chances of you actually having a fall that you can go out and investigate, even though we've got some great terrain like Dartmoor, etc., okay, is going to be very low. So no, I've not yet found my meteorite. Okay? And I kind of realized this a few months before that, maybe 6 months, a year before that. I was unlikely to find my own meteorite as part of the local meteorite network. So I thought, look, I'm going to have to do something different to get my hands on a bit of space rock that I've always wanted since I was a kid. Okay? And I came across this whole classification of meteorites I didn't even know existed. It's not even on that chart that I showed you at the beginning. And these are micrometeorites. Okay? So there is a whole classification of micrometeorites out there, and I'll talk about them in the second part of this, that anybody can go and find. Okay? And I'll talk about a research, project that I'm just launching in Plymouth at the very end, which is hopefully going to engage the local community in finding these micrometeorites. Okay? And this, just for reference, is my first micrometeorite. It's what's called a Bard-Olivine micrometeorite. And that will remember, it took about 6 months of me searching, finding, pulling my hair out, screaming, etc., until I actually conferred my first ever micrometeorite. I have loads now. I have 30 odd micrometeorites in my collection now, but that's always still going to be my favourite, okay? Because it was the first one I found, okay? So what are micrometeorites? Well, the first thing to be careful here is micrometeorites. Yes, they're small meteorites. They're about 1/4 of a millimetre in diameter, so less than the width of a human hair. They can get a bit bigger, up to about 1/2 millimetre, okay, and also a lot smaller as well, okay. So less than, you can get them down about 10, 20 microns in size as well. So there's a big range, but they are small. Okay? The important thing to note is they are not the product of meteors or coming through our atmosphere. They're not the product of breaking up fireballs, raining down really fine stuff. They are a whole classification by themselves. They are what we call, or is referred to as cosmic dust. There is literally dust in our solar system that has been formed by, in the early parts of the solar system, lots of asteroids or comets colliding with one another and creating a dust cloud. And that dust cloud, okay, majority of it is from the meteor zone, is working its way into the inner solar system. And our Earth is constantly going through that. And that material is slowly making its way quietly, silently, through our atmosphere and falling down on the planet. And it's estimated about 14 tons of it gets through the atmosphere and lands on the planet every single day. Okay? That's only about 20% of what actually enters the atmosphere, okay? But it makes it through and it lands. How does it make it through? You think small, it should burn up. It's in a sweet spot of low mass, low velocity, so it does get heated as it enters the atmosphere, okay? But if it's got a low enough mass and low enough velocity, okay, that frictional heating is going to be low enough for it to survive that passage through and to land. And it lands everywhere, okay? One of the best places it was thought to actually find this stuff was to go to really exotic places like Antarctica. Love to go to Antarctica, okay? To go to Antarctica because you could capture this stuff because it's coming through the atmosphere, it's landing, and if you've got a concentration method, as they did here in the Transantarctic mountains, they call them sediment traps. I call them fractures in rocks, okay, where this wind-blown material just gets wedged into those cracks. And you can sample that, and they found hundreds, thousands of these micrometeorites there. Okay? And that was thought for a long time to be the only place, in addition to other places as well, like deep-sea sediments, okay, snow in Antarctica, but also in Greenland, melting large amounts of snow. You can find these micrometeorites in there as well. Until about 10 years ago, when John Larson, okay, and Matthew Genge, who is Imperial here in London, okay, found that you don't have to go to really exotic places to find this cosmic dust. Because it's raining down everywhere, all you need is a large collection area. And that collection area to be collecting stuff that's falling from the atmosphere, aka a roof would be a great place, okay? And then a means of concentrating it. So that concentration could be rain on the water, moving that fine dust particles towards a collection point, aka a drain or a gutter. Okay. So I thought this is simple. So I went up onto my roofs of Plymouth University. Big shout out here for Plymouth University. My office is, no, it's not, it's moved. It's there now. Okay. Went up onto Portland Square. Thought Portland Square would be a great place to go collecting micrometeorites, big flat roof. Turned out to be terrible because it's an asphalt roof. So it's just covered in, and if you've seen asphalt, it's just tiny little bits of rock, okay, and tar. Terrible place to collect it. But other roofs, like over here, okay, and roll building over here as well is not smoother material, and yeah, you can either sweep it up or the material travels and gets wedged by drains. Okay. So I went collecting on there. I also went collecting on big industrial parks outside Plymouth. So this is BD outside Plymouth. Even been down to Goon Hilly. I thought it would be a great place to find micrometeorites down at Goon Hilly, okay, because of its connection with space and space communication. I have actually found stuff down there as well. And also roofs like this. So they don't always have to be flat. Actually, a low-angle corrugated roof is great as well. Okay. And then once you get that material, okay, you need to get it back, and the first thing you need to do is you need to sieve it. Okay, because these micrometeorites are a certain size fraction. So you sieve it, okay, you wash it first because it absolutely stinks, okay. Then you sieve it to a certain size fraction, okay, and then you magnetically separate out, okay, the magnetic fraction. Now I know I said in the earlier one not to use a magnet, okay, because a magnet can destroy the remnant magnetism of meteorites, which is important. In this case, we use it because it's the only way to concentrate up the material. And all of the iron micrometeorites have essentially iron in them. They're either iron oxide or they're iron magnesium silicates. So it's a great way of concentrating them up. Okay? And then you have to go picking. So it's a bit like 4-arm picking. So you just go through your sediments. Instead of picking out 4 arms, okay, you're picking out micrometeorites. Okay? And once you pick them out, okay, you have what are called a series of candidates. And then you can use really nice, so a lot of people use this John Larson's setup here, use light photography, and you can get some absolute stunning images of the different classifications, or in this case, of the silicate group of micrometeorites. Okay? And they make great photographs. Some of these have been turned into artwork, okay, and sold online. as artwork. Some of the more detailed surface morphology ones make some brilliant artwork. Okay? I don't do that because it takes a little bit of effort and there's too much time to set up this light microscopy. And I work at a university, okay? So I have access to an SEM. In this case, this is a benchtop SEM. So I just stick my samples onto a stub and I look at them under an SEM, okay? And my students do as well. Okay? That's a benchtop one, okay? Unfortunately, our one doesn't have an EDS in it, okay? So if I want to chemically analyze them, which is the final stage of actually proving they're a micrometeorite, I go up to the Plymouth Electron Microscopy Centre, PEMC, okay, and use their system up there, okay? And just for reference, this is Greg Welsh here. He was actually an A-level student who came to work with me last summer as part of the Nuffield Science summer placement, so he was paid to come and work with me for 2 weeks, and he found 4 micrometeorites in 2 weeks. Took me 6 months to find my first one. Okay. He found 4, okay, in 2 weeks. Okay. It was all down to my processing. I'd worked out how to process them better. Okay, that's what my excuse anyway. So what have I found? Well, I found, so this is a beautiful example here from the library roof. This is a porphyritic olivine micrometeorite. Another example here, this is from Secure Innovations outside Plymouth, another barred olivine one here. BD, which I mentioned, another barred olivine. This is a cryptocrystalline one, also from BD. Okay, it's called cryptocrystalline turtleback because this morphology looks a little bit like the back of a turtle, the shell of a turtle. And one from Kawasaki, this is a scoriaceous type of micrometeorite. And then from Goonhilly, a beautiful vitreous type here with a nice iron bead. So all of these are what we call silicate type micrometeorites. They're all compositionally very similar. Okay, so they made of silica, magnesium, and iron. Okay, but they all have these different surface textures, from porphyritic to completely vitreous. So why do the micrometeorites have these different surface features? Why are they classified differently? Well, it all comes down to the temperature that they've experienced as they've passed through the atmosphere. So the porphyritic and the scoriaceous type, scoriaceous, should point out, is is usually very volatile rich. Okay, so that's why you usually find these, and they're usually quite holy. Okay, they usually have lots of holes in them. Okay, where volatiles have escaped during that heating process as well. And then you have the porphyritic, which is essentially they've kept its crystalline structure with a thin veneer of melt over the top. And then you go into the barred olivines, higher temperature. Then cryptocrystalline, they've virtually lost all of their original crystallinity. But I like the turtlebacks. They kind of look nice, like these little triangular shapes. And then finally to the purely vitreous, so that literally glass. Okay, they've been the highest degree of heating. And as I said, all of them virtually have the same chemical composition, and they're grouped together as these silicate micrometeorites. But they're not the only types. Okay. Before I get on to the other types, I should point out as well, some of them, what you'll see is, in addition to the overall surface morphology, this is one of those porphyritics again, you can just see some of the original crystals here, and there's a thin veneer of melt over it. What you get, okay, is lots of other surface features here. In this case, lots of dendrites. Okay, so this is iron oxide, which was originally probably iron sulfides in those meteorites, or micrometeorites as it was coming through. But as they was heated, the sulfur got driven off as SO2 in the atmosphere, and the iron oxidized and then recrystallized on the surface. So you get these beautiful dendrites of iron oxide. Okay? Makes great, if you've got an SEM, get some great photographs here of what, and then you tweet them, or you send them, also you send them out on social media as little Christmas trees, because they look like little Christmas trees. Okay, so that's what my social media tweet was at this time. But you can see them in the, not just in the porphyritic. There's another porphyritic one here. Here's a scoriaceous one with the same thing. So you get these really bright dendrites. But you also see some other bright spots as well, which don't look so much like Christmas trees. Okay, and these are similar to these things up here. These are metal beads, because as this meteorite is heating, some of the metals within there, okay, can phase separate and then re-solidify as metal beads. And those metal beads can be anything from really boring iron oxide. You can get iron-nickel alloys together, so that's an iron-nickel alloy one together, which we analysed. You can find cobalt. Cobalt's quite interesting as well. Find these little dots of cobalt. That's what some of these really brighter star ones and triangular ones here were. This is cobalt. And then you get other ones. You get chromium as well, and interestingly, platinum group elements. So some of these meteorites have platinum group elements in them, and they've been concentrated by this heating mechanism. Okay. But these silicate types are not the only type. But there's actually three types of micrometeorite. There's the S-type, which the vast majority of all micrometeorites are. Okay, this S-type. But there are two other types. There's the I-type, or the iron type, which is essentially just iron oxide. Okay? And there's what's referred to as a G-type, which is somewhere in between the silicate type and the iron type. And they're the three main types of micrometeorite. But the vast majority of them all seem to be compositionally the same, the S-type of micrometeorite. And that tells us something that also helps those that are researching this a bit more than I am, helps us understand something about the origins of these micrometeorites. So the majority of the original source material for these micrometeorites are believed to be a group of meteorites called carbonaceous chondrites, okay, which are a really early form, or a basic form, maybe basic's not the right word there, a form of asteroid, okay, that's not been from the early solar system. So the original material of our early solar system, which was coalescing together to form those asteroids. The majority of micrometeorites seems to have come from that material breaking up as they were colliding or being destroyed. Okay. There are I-type micrometeorites. And if you go to somewhere like the trans-Antarctic sample set and you look at them, okay, you will find between about 10 to 20% of those micrometeorites are I-type micrometeorites, this iron oxide type. Okay? So they are definitely falling through the atmosphere and landing. Do we find them in urban environments? Well, we can. They should be there, okay, because there's no fraction, there shouldn't be any fractionation of those micrometeorites as they're falling down between the S-types and the I-types. So they should be in the urban environment. The problem is, and I should say they have been found, so this is an example here of an urban I-type micrometeorite that was found by John Larson. The problem is you're looking for a needle in an even bigger haystack if you're looking for these I-types. And the reason being is we do so much industrial, recreational activities which creates round metallic spherules, balls. Okay, so cutting metal, welding, you're generating liquid metal, that metal is being thrown up, it's solidifying and it's falling back down. Okay. And these, as we refer to as wrongs, okay, this is what I picked out for the first 6 months of this project, okay, and nearly gave up on. Okay, I was distracted by the small shiny things, okay, which are what these were. Okay, so they are there. It's just really hard. It's really hard to find them. Okay? And research-wise, well, why are micrometeorites important? People always ask me this. Okay, well, there's a whole sphere of research out there. I'm not going to go into detail about it, mainly because I haven't directly contributed to it yet. Okay, so these are other people's work, and there's some, as I said, I mentioned Matthew Genge, Mark Suttle, Open University now has done a lot of work on this as well. Okay, they've done a whole range of research. Okay, not just on the modern micrometeorites that are falling. Okay, but also on fossil micrometeorites. Because that's the other thing, that's the bit that kind of is going to loop back to what I want to do in the future, is micrometeorites aren't just falling now. They have fallen throughout the geological record. Okay? And it's those fossil micrometeorites that I'm particularly getting quite excited about, because they can potentially tell us, and they are at the moment, tell us about what's happening in the geological record. Okay? Other thing about micrometeorites as well, this is an interesting paper here. They are actually extraterrestrial nutrients that are arriving, and majority of them falling in our oceans. So we think about nutrients that are coming into our oceans coming from, I don't know, Saharan sand being blown in, from nutrients that are being from weathered rocks coming in through rivers. There's actually a source that is coming directly from space. It's got iron, it's got silica in there, it's got magnesium, it's got a load of critical metals as well. So this paper talked about, actually, it's quite a nice paper here, talked about the contribution that extraterrestrial material must be providing to the oceans every year by way of nutrients to ocean biota. Okay. What really excites me, and this is where I'm linking back now to my own research. Remember I said I'm a paleoclimatologist. I've been interested for years about how past climate change has actually impacted the geological record and what we can understand from that when it comes to current and future climate change. Well, a recent paper used iron micrometeorites from the fossil record, and importantly, something that happens to those iron micrometeorites as they pass through the atmosphere. Because as they pass through the atmosphere, they start melting. And that melting means that actually oxidation starts occurring with the iron. So they start interacting with the oxygen in the atmosphere, be it now, 10 years ago, to 200, 800 million years ago. Okay? And so you're capturing a little bit of a record of that oxygen in the atmosphere. And what this paper has shown is that if you, and I'm not going to go into huge amounts of detail about this, but if you look at the oxygen isotopes in those iron micrometeorites, the 16, 17, and 18, they are going to have different isotopic values depending upon how much CO2 was in the upper atmosphere at that time. So the CO2 concentration in the upper atmosphere affects the fractionation, we call it, of those 3 oxygen isotopes, and that gets recorded in those micrometeorites. So I'm really excited about this because there's lots of proxies to reconstruct atmospheric CO2 values back through the geological record. Iron micrometeorites is potentially a new proxy. And this proxy is global, as long as you can find them. So you're not using necessarily having to just use a marine proxy or a terrestrial proxy. This is a global proxy. They're all falling down everywhere. The only downside is that you need to make sure that those iron micrometeorites have not, once they've landed and interacted with the atmosphere, they haven't been altered by post-depositional alteration. And that there is a way to actually look for that. You look for manganese in them. If they've got manganese in them, it's probably interacted with pore fluids. If they haven't, you've probably got a pristine record. And they showed in their paper that you can do that. And I'm really excited about this because I can now justify my existence back to my line manager and say, actually, micrometeorites is not just completely a wild goose chase by me. It actually has paleoclimate implications as well. So if you want to get involved, and I'm coming to the end now, if you want to get involved in this part of my talk, so look for micrometeorites, there's lots of citizen science sites out there. So John Larson, he's got his own Facebook site. There's others, micrometeorites. And I've been trying to push the boundaries. Don't laugh. I've been trying to push the boundaries here by creating some other social media. So this is a TikTok video. I created one summer because my kids were away in Ireland and I had nothing to do. So I thought, let's create a TikTok video. It'll go nowhere. And showing how to use household appliances to actually collect micrometeorite material, so gutter stuff, how to process it, and how to, once processed, so it looks a little bit like I'm going to go gold panning now. All I'm doing is I'm trying to get rid of the organic matter. So literally by swirling, I'm getting the lighter organic matter to come to the top, and then I'm just draining that off. The heavier, which the micrometeorites will be in, will be falling down. You let it dry, in this case, stick it on a piece of paper, and then I use a strong fishing magnet. I didn't know such a thing. I didn't know there was such a thing as fishing with magnets until I found this. Okay, and then you're separating out the magnetic fraction. Now, from that magnetic fraction, you pick through using a microscope. In this case, this is a microscope that I've got at home, and I was lucky enough, this came from my roof, to actually find a micrometeorite. So that's what they don't look like. These are these wrongs. That is a micrometeorite. And then anybody who's done any micropaleo knows how to pull these off, okay, and stick them onto a stud, and I've got an SEM. I would say I didn't really expect that video to go anywhere, okay. It's now over 500,000 views, okay, on TikTok. If you want to laugh and you're on TikTok, okay, go and watch it, okay, and read the comments, okay. Amazing, okay. It's one group out there thought I'd found the first evidence for government. Have you heard of chemtrails? It's a bit where they spew out chemicals in the planes, okay, to control us all. Okay, this was the first physical evidence I'd found of it. And regardless of what I said, okay, they would not believe me that it wasn't. Okay, and I had another group who kept telling me it was just, I had an asphalt roof, which I didn't, and I was just looking at little bits of rock. And I kind of pushed back on them and said, I'm a geologist, I can tell the difference between a rock and a micrometeorite. Okay. And if you want to get some more information about this, I said I've got a public outreach website, PlymouthMeteors.com. And then, yet again, just for fun, I wanted to learn how to do different things. Kids get a bit embarrassed about this. They're 18 and 16, okay. But I do have a TikTok account. I do have a YouTube channel. I've made some YouTube videos. I even made a Spotify one, okay, which I took a paper and asked an AI to actually make a podcast of it. I'm open about it. It is AI that created this, and it's not my work, so I cite the actual original paper as well. And it created a really good podcast with two people talking to one another about the science behind that paper. I was really impressed with it. And I also have an Instagram account as well. So if you want to know more, please feel free to look at any of those. And then finally, as I mentioned, the university has finally, they either had two choices. They either could sack me, okay, or they could just say, look, give him some money and get him to take this a bit further. So they decided to give me some money, okay, and we're launching down in Plymouth, Cosmic Dust in the City, which is an outreach program where I will be engaging local communities, okay, so schools, museums, community groups in the search for micrometeorites, okay. And that's not, I should point out, that's not the first. There are other examples of this throughout the country, okay, and globally as well. There's another example in Cardiff where there's a local engagement group as well. And the university has officially launched it. They're launching it tomorrow, okay, which I thought was a great idea until I realised what date I'd picked. So tomorrow morning, I'm going on BBC Radio Cornwall, if they still have me, okay, the breakfast show, to talk about the search for cosmic dust, okay? And if that does not start off a whole conspiracy theory or an April Fool's thing, I don't know, okay? And I also have to quickly get changed. I'm going to do a spotlight, so it's our version of regional news, BBC Regional News down in the southwest. I've got to go and talk about micrometeorites there. Interestingly, they asked me to bring some props with me, and I thought, well, can't really bring a micrometeorite. So literally, I'm bringing a dustpan and a brush and a really big magnet, okay, and I'm going to talk about the project and how people can get involved. And the idea is it's not just about finding these. It is about finding them because they will go into an archive. That archive would then be used for research in the community, the scientific community, okay, because you need lots of these to do research on. But it's also to help students understand a little bit about science, about the cosmos, about chemistry. What is the chemistry of these things? So it's about engaging them with that as well. So thank you very much. I hope you enjoyed the talk. I actually stuck to time this time.
You did. Thank you.
So yeah, not bad.
Okay, so Steve's very happy to take some questions from you in the room or online. So you've got a question in the room, please put your hand up and we'll get a mic to you. We've got a couple already down the front, and if there are any online, Alicia's going to read them out as well. So we'll start down here.
I have two questions.
Okay.
Do you get to keep meteorite finds is one question. And my other question, when you were talking about micrometeorites, we have actually been to asteroids like Rosetta. Are the materials from Rosetta like micrometeorite materials?
Okay, in answer to your first question, do we keep meteorites? I suppose if a meteorite is found on land somewhere and you were to find it, it actually belongs to the landowner. So you're not allowed, in the UK anyway, you're not allowed to take that meteorite and claim it for yourself, okay? So in the case of the Winchcombe meteorite, the landowners, in other words, the person who owned the house and also the farmer's field, they donated it to science. So it went to the Natural History Museum and research could be done on that. So technically they own it. When it comes to micrometeorites, if it's on your roof and you find it, it's yours, okay? And as part of this project, I'm going to try and engage lots of people to find that material. Whether they would want to keep it afterwards, bearing in mind you need a really powerful microscope to see it again, probably, I'm hoping they will donate it to an archive. So I'm starting an archive in Plymouth, and I think the plans by the micrometeorite community is to have a national archive. So one created and controlled by the Natural History Museum, but maybe with regional collections that donate to them. So my hope is that they will allow them to be used for research that way. When it comes to the Rosetta mission, yes, that is an example of a capture. One of the aims, so this podcast that I mentioned, that I took this, I did an AI podcast from that paper, was a white paper that was written by the micrometeorite community. And in there, they talk about micrometeorites potentially being used to help plan future capture missions to comets or meteorites, okay? Because compositionally, I'm getting a little bit outside my field now, but there's a similarity compositional-wise between what's in the micrometeorites and potentially where future capture missions can happen in space. So they're talking about, yes, if we have this archive, we can prepare better for these future capture missions.
So,
Sorry, if you just wait to have a microphone.
like
If you just wait until there's a microphone so the people online can hear you.
So what you're saying is that when you have a really good archive, the next time we land it on something like Rosetta, we'll be able to understand the composition better?
Potentially, you've got to bear in mind that what's coming back from Rosetta was pristine material. What's come through the atmosphere as a micrometeorite has been heated. So it's going to have suffered a degree of alteration there. So it's never going to replace doing these capture missions in the future, but it could help plan. I think they're talking about helping in the planning phase for future capture missions.
We have a question from online. Is there any other organisation which could be contacted apart from UK Meteor Network or Natural History Museum for help in classification of a UK meteorite, fossil tektite, micrometeorite, or even remnants of a UK meteorite impact site?
I may have to ask a friend on this one. Okay. I would always suggest that they contacted the Natural History Museum is the first port of call. They have experts in working with meteorites, okay, and they would be able to help in the classification of it. When it comes to micrometeorites, there is a lot of micrometeorites being shown online at the moment. In Facebook groups, some of these Facebook groups are people are sharing their images of micrometeorites, and the community is helping to identify those. So they could try some of those. One of the ones I mentioned in one of my slides. I would say though that some of the stuff that's being shown, I personally would be a bit dubious. I think you definitely need the SEM to see clearly the surface structures more clearly, and you need the chemical analysis to demonstrate it is a micrometeorite. So,
Thanks.
thanks.
Okay, one over here.
The micrometeorite fossils, because of the trying to keep them preserved enough to hold the information, does that then sort of open up a bunch of challenges, and certain like units of rock would better preserve it? And then while I was waiting, I was thinking that would sort of local or even potentially quite far away, like volcanic activity, produce a lot of material that would sort of muddy the record and would look very similar?
Yes, so everything in the fossil record, in the geological record, is potentially could suffer post-depositional alteration. So, classic example, foraminifera from the microfossil community. Okay, for them to be a reliable tracker of past climate change, ideally that you don't want them modified. Okay, so the same thing is being shown. I've seen some recent research coming out of Imperial that's showing that the micrometeorites, there is a high percentage of those that are being discovered in the geological record are suffering post-depositional alteration. Okay, so you're getting this manganese, I think it is, that's been incorporated within that and indicating that they could have been altered. They seem, the work that's been done so far tends to concentrate on carbonates, so chalk or limestone, because it's, there seems to be a higher probability of preservation in there, and they're also slightly easier to work with. Okay, but mudstone they'll be found in the IODP cores, okay, in mudstones from deep sea oceans as well. So, is there a preferential environment? You wouldn't want any kind of geological process. So, if you're looking for micrometeorites and material that's been through, I don't know, an orogenic mountain building event, there's a chance that they could have been. There's lots of fluids associated with those. They've got a greater chance of being diagenetically altered. So, and then your final bit was about volcanoes. Yeah, there is, if I remember right, there was a recent paper. There's a class of what look like iron micrometeorites, but are actually being generated from. Oh God, I can't remember now. Yes, there is volcanic activity that can generate small metallic spherules. Okay. There's also tektites, which look a little bit like micrometeorites. For those that don't know, tektites are when a big asteroid hits the Earth, melts stuff, that gets thrown up into the atmosphere and that falls back down again. Okay, it can look like it's come from outer space, but it's actually originates on the planet. So yeah, when it comes to the fossil record, you have to be a lot more careful about making sure what you classify is actually a micrometeorite. Before you even get into the stage of looking to see if it's diagenetically altered or not. So, yeah, I say it's a project I want to get involved in, but I think I may employ a few PhD students to do that. No, I'm happy to do it. So.
Question with the scarf in the middle.
Hello. The oxygen isotope thing. Can you say a bit more, explain a bit more about what it is about the ones from the micrometeorites being like global proxy versus like something where you found it like terrestrially or something like that, like what the difference is, and
Okay.
and then also how much dirt did you have to take off of your roof for the TikTok? Was it quite a lot?
Okay, so with respect to the fossil one, sorry, I'm concentrating on dirt now. So the fossil one, yes. So what I like about this potential new CO2 proxy is that existing proxies use, for example, a foraminifera and boron isotopes in foraminifera to reconstruct atmospheric CO2, or they use plant leaves and stomata in plant leaves to reconstruct atmospheric CO2. And while you don't need many global locations to get an atmospheric CO2, global atmospheric CO2. There's always going to be parts of the record that are going to be less chance of preservation of that material. Okay. With micrometeorites, if it's constantly raining down, so you've got this constant flux, and there doesn't seem to be much change in this flux over time, bar for a couple of events. There's an Ordovician event, which is really interesting, where there's an increase in the flux of micrometeorites, possibly due to some asteroids hitting each other, breaking up, and then raining material down on us. If you've got that constant flux coming down, in theory, you could, if you've got the right preserving rock types globally, you could find this material, extract it, and get a CO2 signal. It literally it's just been validated in the last year or so. I've not seen any long-term records. I've been thinking of a few, going back to my PETM example, and I thought that could be a good example of doing it, because one of the problems with that event is it's an ocean acidification event. So you lose a lot of your proxies at the very start of that event, because you can't reconstruct atmospheric CO2 on 4 amps using boron isotopes if they don't exist, because they've disappeared. But if you've got some micrometeorites that have been landing at the same time, then possibly you could use those. So that's what's got me excited about the project. And then getting to dirt, yep, I collected lots and lots of dirt. I literally came back, so I came back with sample bags. So when I first went, sample bag about that big, full of dirt off a roof, and then, started processing that. And nobody here has probably processed roof dirt before. Let's just say it's organic rich, so it does hum a bit, especially when you start. I really wish I lived in a really dry, arid environment like some parts of the US, because literally they just go up onto the roof and they just have the magnet, and they sweep up their dry sediment and just do the magnetic separation on the roof. You can't really do that in the UK if it's wet at all, because those micrometeorites are probably adhered to bits of organic matter that's in your gutter or on the roof as well. So you'd be losing lots of material. So in the UK, anyway, and a lot of other places, we just collect everything and do all the processing in the lab. So.
Okay, in the interest of time, we've got quite a few hands up. So if there's no final questions online, I'm going to give the final question to the gentleman down the front. And for those of you that have still got questions, please stay and join us afterwards for a drink. And I'm sure Steve will be happy to answer them over a glass of something as well. So.
These micrometeorites are spherical because something coming down got very hot, turned to a little ball. So they're really hot at one point. During their trajectory through there, do they actually then cool? You know, when they're small enough, do they actually, by the time they reach the ground, get in equilibrium with the atmosphere around? Or are they still hot enough to interact with material when they hit? I was thinking, basically, if they land on a sheet of plastic, do they bury themselves in?
No, they are, I believe. Okay, they're not all perfectly round as well. Some of them are, you get elongated. Very rarely you get a teardrop-shaped one. I always thought they would be teardrop-shaped, but then I was thinking about something that's coming through the atmosphere that's doing that. And they are rounded, but I would call them sub-rounded. If they're perfectly round, look like a football, okay, they're generally wrongs. Okay, they're not. Okay, but by the time they've travelled through, because it's the heating is minimal and the volume is minimal, they cool really quickly in the atmosphere. So by the time they've got down to the ground level, they're solid. The only difference would be if they're in the geological record, so they've been deposited. If they're staying there for thousands to millions of years and interacting with fluids around them, then you can, and then there's any small fractures or breaks in them, you can get fluid ingress, and then you can get alteration. But that's over a long period.
Okay, but basically, I've no point in me taking the plastic sheet off my roof and trying to investigate for buried ones that sort of melted themselves in.
I don't think they wouldn't have melted themselves in. Okay.
Okay, if everyone can join me in thanking Steve once again. Okay, for those those of you online, thank you very much for joining us this evening, and we hope we'll see you at a future public lecture. For those of you in the room, the evening is not over yet. There will be a drinks reception just back into the lower library through those doors at the back, so we hope that you will join us for that and continue to ask questions and chat to everybody else in the audience. Our next public lecture is on the 21st of April, and the title is Pangea on Acid. It's being given by Professor Kathy Benison, who's actually visiting us from the United States. She is the international lecturer, distinguished lecturer from the Geological Society of America, so we're very proud to have her joining us on the 21st of April, and we hope that you will join us for that one as well. So thank you very much, and enjoy the rest of your evening.
Thank you.